Now let's look at what we will be defining as inductance. So we have seen that if there is a changing magnetic field, it will induce an electric field. If it will induce an EMF. So let's say we have some circuit element over here. And nearby we have another circuit element. So let's say we are studying this one. The EMF around this surface circuit element will be minus the magnetic flux divided by dt. Now, if you change the current in this left circuit, and if you send the current through this left circuit, it will create a magnetic field, which will create a flux passing through this circuit element, this loop. And if you change the current over here, the flux over here will also be changing. So it's kind of, it would be interesting to study how does the flux passing through my right second circuit depends on the current running through my first circuit. Let's say this is my I2, my circuit 2. The flux, let's call that 1. Well, first of all, we know that B created by this second ring will be equal to curl of A, which is mu 0 over 4 pi I times dl over R1 minus R2. So this is the B at the point R1. R1 is some point over here. So I'm basically calculating the magnetic field at the point R1 in this right-hand loop will be equal to curl of the A created by the left-hand loop. And the A created by the left-hand loop will be just mu 0 over 4 pi. The curl of the A is mu 0 over 4 pi times the current running around my wire times dl over the distance. So you see, in part, then the flux phi B1 will be equal to B created by 2 at the point R2, R1, dot ds, let me put the 1. But you see, this is proportional, B is proportional to I2. So this flux is proportional to I2. And if we factor out that I2, what remains does not depend on the current. And that we will call L, let's say, the inductance of 2 on 1. It's called mutual inductance. And it is defined as L21. This is equal to curl of mu 0 over 4 pi. I2 is not there anymore. Let's say this is dl2 over r1 dot r2 dot ds1. But you see, I have the surface integral of the curl of a function. I can also convert it to a loop integral. So this is equal to dl1 dot dl2 divided by r1 minus r2 times mu 0 over 4 pi.
Double integral?
Yes, it's a double integral. But you see, if I exchange 1 and 2, that is the mutual inductance of the first loop on the second loop, well, nothing changes. So this is equal to L1, 2. Which one? Well, you see there, I have a surface integral over here of the curl of a function. I converted that into a loop integral. That is what dl1 is about. Because curl of a dot ds1, I just said that this is equal to a dot dl1.
Şimdi bu dl1, dl2 hangi sinüsünde oluyor?
Well, dl1 is over here. Let's say this is my dl1. This is my dl2. You see, when I'm writing A, I'm integrating over this loop. When I'm writing the phi, I already know B at the position of my first loop, loop 1. I integrated over the surface of loop 1. Well, you don't usually use this relation to obtain L12. But it's interesting to note that the mutual inductance basically depends on the geometry of your system, the shape of your loops, and the relative distance between your loops, and nothing else. It doesn't depend on how much current you pass through the loop, etc. It only depends on the geometry. And the mutual inductance, the inductance of a circuit 1 on circuit 2 is the same as the inductance of circuit 2 on circuit 1. So whichever one is easier to evaluate, you can just use that one.
Hocam mesela bu iki ringi böyle üst üste koyunca sonsuza gidiyor.
Let's look at an example. Well, one thing that is easy to evaluate was the solenoid. Let's take a solenoid. What is the direction of B? If the current is running in that direction, downward. Do you remember the magnitude of P? It was mu0 times I times N. N being the number of turns per unit length. Now let's imagine we have another single loop or double loop just around it. With radius, let's assume R.
İki tane şey mi var?
It just goes twice. The radius of the solenoid is R1, the radius of the outer ring is R2. So what is their mutual inductance? Well, to calculate the mutual inductance, we have to calculate the flux going through one of them when we send the current through the other one. Let's say I1. Or phi 1 is equal to L21 I2. Whichever one you like. You can either assume that there is a current running in the outer loop And then it will create a magnetic field, which will create a magnetic flux in the inner solenoid, and you can calculate the total flux in the inner solenoid. Or you can assume that you are sending a current through your solenoid, and which creates a magnetic field, which creates a flux in the outer rings. Well, the second one would be easier because we already know the magnetic field of the solenoid. It is uniform. So calculating the flux for this B field will be just easier. In the other case, the magnetic field created by the outer rings will not be uniform. It will be quite a complicated task. But we already know that it doesn't really matter which way you go. You send current through one of them, calculate the flux going through the other one. So let's see, phi2 is equal to, well, you see, this is our system. This is my solenoid. Let's see, I'm looking from the top, so this is the direction of the current I. And outside, I have my rings going around twice. So this is R1. This is R2. And the B field is over here. And not outside. So what is the flux in my outer ring? So this is my B, mu 0 I n pi R1 squared, because outside this radius R1 there's no B field. And within this radius R1, B is uniform. So I can just multiply B and the area times 2. Because there are two rings. Each one has this flux, this part. Since I have two rings on the outside, I have the total flux passing through both of those rings is multiplied by 2. And this is, let's say, I1. This is equal to pi R1 squared times 2 times mu 0 n times I1. So here you have L12, which is also L21. Independent of R2, you're right.
Dışarıdaki ring de n kadar.
Well, if it rotated n times, n rings, so here we would have n, and here we would have n. Or let's say n2 rings. n2, n2. So L12 or L21, which will be equal to pi R1 squared times mu 0 times N1, N2 over L, where I defined N to be N1 over L.
Hocam bir şey sorayım. Şu ta başta burada mesela şu çubuklu şeyde 2 tane dönme olsaydı o zaman bunu 2 ile çarpmak.
Yes. Or if you think it in terms of the EMF, if one loop gives you an EMF, let's say epsilon 0, two loops will give you an EMF twice epsilon 0. Because each loop will do a work of epsilon 0 on your unit charge. So if you have two loops, well, it will do twice the work. Well, let's go to our previous exam. Any questions on this?
L dedik ya, L
We just assume I took a length L of my solenoid, and which has N1 turns. Well, the reason why I wrote it in this form is, well, we already said that if you change the solenoids, it should be the same. So here you kind of see that symmetry between N1 and N2. Well, that symmetry is not so obvious over here, but still we already know that it should be symmetric. Now, let's go back to over here. We calculate this induced EMF. Okay, basically, we need flux to calculate the induced EMF. That's one thing that we will need. But you see that the induced EMF is non-zero at S is equal to R. So what is special about S is equal to R? Well, S is equal to R is where my solenoid is. So there I have my solenoid which carries a current, and I'm changing the current and hence changing the magnetic field inside. And since there is a magnetic field inside that is changing, it creates an electric field on the solenoid. This additional, well, there's already one electric field created by, needed for this motion of the charges. But now there's this induced electric field also on the solenoid. And hence there is an induced EMF on the solenoid itself that is creating the changing magnetic field. So you see here we were looking at a case where the EMF in a given loop was created by the current in another loop. But it doesn't have to be two different loops. If you just take this one, if you try to change the current, there is an EMF at that point due to the changing magnetic field created by that thing. So that is called the self-inductance. So if you just take your circuit, there is a current running through your circuit. There will be a flux passing through your circuit, and that flux will be proportional to I, the current passing through the circuit, and the proportionality constant is called the self-inductance. And the EMF will be minus L di by dt. So this loop over here, or which is also called an inductor, it will also create an EMF in addition to the EMF that your battery or your source is creating. For example, you can have such a circuit. So at a given time, you close your battery, you close your switch, and then if you consider a unit charge and the work done on a unit charge as it's going around the circuit, well, as it goes from the negative terminal to the positive terminal, the work done will be V0 per unit charge. As it is crossing your inductor, the work done on your charge will be minus L di by dt. As it's crossing the resistor, it will lose some energy, and that energy will be minus I times R, the amount of energy that your unit charge will lose. So this should be equal to 0. So this is how your current will change as a function of time. True. Well, let's see. Let's solve this equation and let's discuss it. I will just write down the solution. I would be equal to V0 over R times 1 minus e to the power minus t over tau, where tau is equal to L over R. This is the solution, assuming that at t equal to 0, there is no current passing through your system. Because the switch was open, no current was passing through. And so if you look at the shape as a function of time, so this is our V0 over R. Well, if there were no inductor, the current passing through the circuit would be just V0 over R. But now, at t equal to 0, it starts from 0, and it slowly approaches V0 over R. So at sufficiently long time, you see the current is just constant, so that the I by dt term is negligible. You ignore that after a sufficiently long time, and hence you obtain the current is V0 over R, as if there were no inductors.
Yani kapasitör gibi böyle doluyor mu?
Yes, in a sense. It is filled with magnetic field. And the next question would be, of course, if it is filled with just like a capacitor, does it store energy just like the capacitor?
Manyetik enerji.
Yes. Let's say we know that epsilon is equal to minus L di by dt. So how much energy do you store? Power is just epsilon times I. Epsilon is the work done per unit charge, while power is the work done per unit time. So the total work done per unit time, you have to multiply epsilon by per unit charge, divide by per unit time, but that is I. This is equal to minus L I di by dt. But this is equal to minus d by dt L d squared I by, no, d by dt 1 over 2 L I squared. This is the work done. No, this is the power. The work done is minus, no, let's say plus 1 over 2 L I squared. Now, what happened to the minus sign? This is the power of the inductor itself. So if you want to increase the current from 0 to some final value I, so from 0 to I, you know the power, just integrate it over time, you get the total work done. If you integrate power over time, you get the work done. Now, this is the power of the inductor. It's the work, if you just put in that power into this integral, what you obtain is the work done by the inductor. But the energy stored in an inductor will be the work done by other things. So the battery is pushing the current against the inductor. The inductor doesn't want that change. So that is why I add this minus sign over here. So the work done on the inductor is 1 over 2 L I squared, or the energy stored in the inductor.
Yani induktör kendi üstüne iş yapmıyor mu?
it is doing work. The work that the inductor does is minus 1 over 2 Li squared. But the energy stored is the work that you have done on the inductor, or the battery has done in this case on the inductor. Now this is similar to Q squared over 2C in the case of the capacitors. But if you remember our discussion of the capacitors, we started with this expression and we saw that we can in fact relate it to the electric field rather than on the charges. We can do a similar thing over here. This energy seems to be the energy stored in the current, but we can relate it to the magnetic field. It is actually the energy stored in the magnetic field. So let's do that. 1 over 2 L, well, let's see. First of all, let's start with the definition of the capacitance, the inductance, sorry. Phi is equal to L times I. Well, on the left-hand side, phi is nothing but P dot ds. This is just L times I. So the energy stored, let me just use E, not the magnitude of the electric field, but the energy stored, will be equal to 1 over 2 times L times I, which is 1 over 2 B dot ds times I, which is equal to 1 over 2 curl of B, curl of A dot ds times I, which is 1 over 2 A dot dl multiplied with I around the closed loop, or this is 1 over 2 around the closed loop A dot I dl. Well, we can also take a, you see, in this example, we started with a current carrying wire. That's why we ended up having this I times dl. But we could have just started with an arbitrary current, volume current density. In that case, this expression would have been just integral of A dot J over the volume. You see, compare this with so basically, we have the same expression. Instead of the scalar potential, we have the vector potential. Instead of the charge density, we have the current density. So this was kind of motivating that expression, all these discussions. And this factor 1 over 2. It's exactly the same factor 1 over 2 here, and exactly the same factor 1 over 2 over there. What is J in terms of P? What was curl of P? Mu 0 J. So J is nothing but 1 over mu 0 curl of P. One over 2 mu 0 A dot curl of P. Now it would be nice if we could move that curl over to A, because curl of A would just give me another factor of P. We would of course get a surface integral. Let's look at this term. Divergence of A cross B. This is equal to del over del xi, epsilon ijk, aj bk, which is equal to epsilon ijk, del aj by del xi, bk, plus epsilon ijk, aj, del bk by del xi. So the gradient of divergence of the curl of B, this is equal to, well, the first thing is the curl of A, the k component of curl of A, the k component times bk. If you look at the second term, that is minus aj curl of B, the j component. Or the divergence of A cross B is equal to, well, this is bk. B squared minus A dot the curl of B. Or A dot the curl of B is equal to B squared minus the gradient of A cross B. We are almost done. We had already seen that the energy stored in the in my inductor was this expression over here. But this is equal to 1 over 2 mu 0 B squared dV, B is my magnetic field, minus 1 over 2 mu 0 A cross B integrated over the closed surface bounding my volume V. Now, if I want to calculate all the energy stored in all the magnetic field, I have to integrate over all the volume. So the surface is at infinity. So if volume is the universe, the total energy stored is just 1 over 2 mu 0 B squared integrated over the volume. So here we have a energy density, the density of energy stored in the magnetic field. Just compare it with the energy stored in the electric field was 1 over 2 epsilon 0 E squared. So basically, just like we can store energy in the electric field, we can store energy in the magnetic field.
Hocam şimdi elektrik field'daki elektrostatik sistem. Magnetostatikte böyle bir şey yazabiliyoruz mu? Manyetik.
Well, this is what we derived. Well, there is one little catch we have to pay a bit attention to. We are looking at time changes, so it's not really magnetostatics. This is what we call quasi-static. Now, it's not magnetostatic. Nevertheless, these are systems that are changing slowly enough so that we can use the results of magnetostatics. Now, later on, we will see that the changes in magnetic field, they take a finite time to propagate. So, for example, if you look at the previous definition of mutual inductance, well, so So will be the case in the self-inductance. By letting phi B1 is equal to some constant times I2. So this we can always say in magnetostatics. This will always be true. But later on we put this in this integral in the expression of Ampere's law. We are talking about time derivatives. So the current is changing. But if the current is changing, it will take a finite amount of time for the magnetic field over there in the other loop will change. It will take a finite amount of time, not zero. So this relation, this definition of inductance over here, well, this definition assumes that the flux, if I changes, flux changes instantly, which is of course definitely not true. But you see, as we will show in next semester, the changes move at the speed of light. So for example, if you just have these two circuits just next to each other, any change in I2 will create a change in the flux in the other circuit almost instantaneously. The time delay will not, you will not be able to notice the time delay. So this is what we mean by quasi-static. It is not static, but we can still use the results of magnetostatics. Because we will see that the corrections will be basically proportional to 1 over the speed of light, which is huge compared for our everyday life.
Peki hocam böyle ikisi uzak olduğu zaman buradaki akım değiştirince elektrik alan anında mı değişiyor?
Well, you see, flux changes almost instantaneously. If flux changes almost instantaneously, then the electric field, there will be an EMF created almost instantaneously. Again, I underline the word almost instantaneously. It's instantaneous for all practical purposes, for most of the practical purposes, but nevertheless, it takes a finite amount of time, because it will move at the speed of light. If it is 1 meter, for example, it will take something like 10 to the power minus 8 seconds. But we cannot measure it for most practical cases. So as a final subject of today, let's discuss the Lenz rule, or law, whatever. You see, we have this one, epsilon is equal to minus d phi b by dt. Well, the Lenz law or the Lenz rule is this one. It's the minus sign, which states that the induced current is in the direction that will oppose the change that created it. So what does this mean? So let's go to our first example of the induced current. The rod is moving. So what is the cause of this induced current? Well, the motion of the rod. That is what creates the induced current. If the rod was at rest, then there won't be any induced current. Yeah. Okay, so first, step by step. The reason that the thing that creates the induced current is the motion of the rod. Okay? So this creates an induced current, but the induced current should be such that it will try to stop this motion. So how can it stop this motion? By feeling some force due to the present magnetic field. So basically, we can use the Lenz's law to say that the induced current should be in such a direction that the force acting on this current should be in minus v direction. And what is the force? I dl cross b. If there is a current carrying wire, the force that a segment feels will be given by this expression. So if I is in the upward direction, B is into the screen, so dl cross B is in the opposite direction of V. So I should be upward. Now that is what we had already obtained. Okay, that is one way of looking at it. Another way of looking at exactly the same problem is that the reason why there is an induced current is that the flux is getting smaller. Well, its magnitude is getting smaller. Okay? So as the rod is moving, the total flux in this loop is getting smaller. So the induced current, which will create an additional magnetic field, should be increasing the flux. Okay. You see, sure, I mean, you see, this is my loop or area that I am considering. You see, there are different ways of looking at exactly the same problem. What is creating the induced current? Well, Sarjan says that it is the velocity of the rod that is creating the induced current. So he says that the induced current should be such as to oppose this motion. And so the induced current should feel a force in the opposite direction of V. So the induced current would be going upward in the rod. That is one way of looking at this problem. Well, I have a different way of looking at exactly the same problem. I'm saying that, okay, there is an induced current because the total flux going through this rectangle is getting smaller. So the induced current should be such that it should try to increase the flux going through that rectangle. So the induced current will create an additional magnetic field. So this magnetic field should try to increase the total flux passing through that red rectangle. Well, if the current is running in the clockwise sense, it creates a magnetic field into the screen, increasing the flux. So just the application of the Lenz's law, Lenz's rule. Now let's look at this solenoid case.
Can we say that the reason of this Lenz's rule induction is the Newton's law or inertia?
Conservation of energy, basically. I mean, you see, if the current enhances the cause that creates it, well, it will keep creating a larger current, which will enhance the cause, etc. So you will get energy out of nowhere. Now let's look at this case. Well, I know that there is no wire over here around this loop, but let's imagine putting a wire. So if there is an EMF created, there will be a current running in the wire. Just imaginary wire. So let's say that at a given instant, I choose the direction of my wire in this direction, so flux is positive in this direction, etc. Okay? So at this instant, let's say that f of t is increasing. So B0 is positive and f of t is increasing at a given instant. Well, that means that the flux is, first of all, positive, because its direction is in the positive direction of z. Secondly, its magnitude is increasing, because flux will be proportional to B0 times f of t. So the flux is increasing, which creates my induced current. So the reason, the cause of this induced current is the increase in the flux passing through my loop. So the induced current should be such that it will try to decrease the flux passing through my loop. But that means it should go counterclockwise, which will create a magnetic field into the screen. Well, that is what we had found. So if f of t is increasing, that is the time that we looked, we found that the induced electric field is in the minus phi hat direction. That's the clockwise sense. Well, let's come over here. We chose our loop to be clockwise. And so the flux is positive if B field is pointing into the screen. So let's again consider a moment in which B0 is positive, f of t is increasing. So the flux is positive or negative? It's negative. Its magnitude, is it increasing or decreasing? Its magnitude is increasing. F of t is increasing. So you see, flux is negative, but its magnitude is increasing. It just means that the flux is decreasing. So it was minus 5 in suitable units. Now it's minus 10 in suitable units. Minus 10 is smaller than minus 5. So it is decreasing. So the induced current should be such that it will try to increase the flux. Well, the flux is positive if the B field is in this direction, so the induced current should be such that it will create an additional B field in this direction. Well, that is, it should be in the clockwise sense, and hence in the minus phi hat direction.
Sistem dengeye gelmiyor çünkü.
Well, the system, it's like, you see, the magnetic field is just like the inertia, in a sense. It doesn't like changes. It tries to stop the changes.
Elektrik field öyle mi peki?
Electric field is like the kinetic energy. If you would just make the analogy with the mechanical systems, electric field is like the kinetic energy, whereas the magnetic field is like the inertia. Magnetic field doesn't want to change. If you are changing the magnetic field, it automatically creates some induced electric fields, which will kind of, whose effect will be to lower the induced electric field, to reduce the change. Well, you can just take this Lenz rule, Lenz law, as a rule of thumb when you are trying to determine the direction of the current, whether it will be increasing or decreasing. So for example, let's say you have a magnet. North pole, south pole. You have a ring. This is closer to you. Now, as the magnet is moving upward, what will be the direction of the induced current? Yeah, you see, B is increasing in the upward direction, right? As the magnet is approaching my ring, B will be increasing in the upward direction, which will create an increase in the flux. So the induced current should try to oppose it. So it should be creating a downward additional magnetic field. So it should be this way. If you look at it from the top, it's clockwise. This side is again closer. Let's say that it crossed the ring, now it's moving in the upward direction, it's going away. So what will be the direction of the induced flux? Well, let's see. The B field at this ring kind of has a vertical upward component, which is getting smaller and smaller as the magnet is going further away. So the induced current will create an upward component of the will try to enhance the upward component of the magnetic field. It doesn't want it to get smaller. So it's just in the opposite direction. So you see, this is your ring. So you see it like this. You are kind of looking at it from somewhere up. Your viewpoint is up. I'm not talking about closer to the magnet. I'm talking about closer to you. You see the ring, all the points of the ring, since it's a circle perpendicular to the magnet, they're at the same distance. You cannot say that one point is closer than the other point. Yes, any last questions?
Hocam şimdi hiç magnet yokken bu şeyde de işte hiç akım yok. Sonra manyetik alanı koyunca akım oluşuyor.
Not when we put the magnetic field. You see, we have this ring. There's a magnet over there, staying over there. There's a magnetic field at this on my ring. Nothing is changing. So there's no induced current. Then my magnet starts to move upward at constant velocity, let's say. It is moving. As it is approaching, there will be some induced currents over here in this direction. Then it enters my ring. It starts to move away from my ring. Then the induced currents will be in the opposite direction. If you put some lamp, let's say, on your ring, you will see that it starts to light. As the magnet is approaching at constant velocity, it's very dim initially because it's very far away. As it approaches, it gets very bright, and then it suddenly dims again. Well, not suddenly, but quite fast. It dims again, and then as it's going away, it gets again very bright, and then slowly dims as the magnet is moving away. It's the change in the magnetic field that's creating the electric field, or the EMF. Not the magnetic field itself.
Is it a useful way to create AC current?
There are easier ways. Well, to create the AC currents, basically you take a loop, in fact many loops, and rotate it in a magnetic field. The angle that the area makes with the magnetic field constantly changes. So the flux constantly changes, creating a magnetic field, creating an EMF. Okay, so see you on Friday.